Hello and welcome to one more lecture on this short tutorial series. Now we are concentrating in differential equations. In the last few lectures I showed to you how important are differential equations for biomedical engineering and engineering in general, of course, but especially because for biomedical, where we use rates, we use variation of things, and a differential equation exists to relate quantities that vary, one with respect to the other when we consider some special variables like the time or the concentration and things like this. And we have showed to you not only a few ways to solve the equations, but also we have shown examples how to deal with the problem, right? How we construct, because sometimes we think that the differential equations, a course in differential equations, we have only to worry about solving, and what's the most important is how to construct an equation that can represent in some sense a physical effect, a system where we can relate the quantities. And we have showed to you how you have to worry about the way to construct those equations. Okay, and we started to implement ways to solve the equation, right? How can we solve the equation once it's constructed? Because normally when we have the solution of a differential equation, we have an analytical expression, or we have a quantification of the variation of the important quantities involving our problem. Okay, but I explained to you what we call the ordinary differential equations, the homogeneous, which is equal to 0, and the non-homogeneous, which is not equal to 0, and explain to you a few of the ways to solve based on the fact that the differential equations normally is variations, and to understand how those quantities really evolve one with respect to the other variable, we have to integrate, we have to add up the variation, so we build up the whole quantity that we are dealing with. But there is many methods, very important for engineering, that help is the solution of the differential equations. And today we're going to continue this showing some more elaborate methods that are not only one methods. Of course, there are numerical methods that we're going to speak a little bit at the end of this tutorial, but there are other methods that are very powerful, very powerful in all the fields of science, and you must know them to be able to solve the equations. So today, I'm going to speak about what we call the method of the power series. I think you all know what's a power series, right? A power series is a quantity or a function that can be written in terms of powers of the variable. So here's the independent variable, x, and this is a function that we can write in terms of powers of x's. This is called a power series. And what's interesting, a lot of functions, most of them, can be written as a power series. In general, functions, and there are methods to expand, we call expansion is in powers. So any function can be expanded in terms of power series, most of them. There are a few that has this special divergence in many places that they present some problem, but in general, they can be presented as series. But that gives us a very interesting thing, because if any function can be written as a power as a polynomial, right? As a series, as a sum of powers of the variable, means that instead of looking for the function itself in solving a differential equation, we can look for the solution as power series. So that's the idea of using a method that's called power series method for solving differential equations. So, but the first point that you should know is that this statement is the basis of everything we're going to say today. That a function can always be expanded in powers of the variable. And the coefficients that appear here, those coefficients, they are very important, because if I know those coefficients, I know the whole function. I know the whole series. And then knowing a function expressed in a power series is basically equivalent to know the function as a whole, because here I can consider many terms. If the x is small, of course, I have to consider only the first part, the first few terms, the lower power, we say. But if it is a function that we have to extend until very big x's, we have to continue until very large values of power of the exponent. Normally, we write a function as series that way. But in a more generic way, right? If we want to say, well, okay, because sometimes it's easier, or is better, or is more correct to express a function in power series, not only in x, but in around a point. So normally, if the function has some properties around a specific value of the variable, here x0, it's better to expand the function around that point. And then instead of express as power of x, we express as power of x minus x0 to the power m, and this sum represents the whole series that we are talking about. So this is a very important part of the mathematics, which is the expansion of functions in series. And there are many ways, and we learn in basic calculus that Taylor expansions is a clear way to express. If functions has derivatives of any order, is more or less like a guarantee that we can expand or express a function in terms of series. And those coefficients, of course, they are related to how important is each power in this series, right? If I have a large coefficient for 1, means that the linear part is important. If I have a large component for square, means that the square part is important. If I have a very large component for 0, the independent term means that the independent term is very important, the overall when x equals to 0 and something. So normally those coefficients, they will express to us how important is each order of the series. Okay, so this is this has nothing to do with the differential equation. This has to do with functions, right? The fact that I can express most of the functions I can express in terms of power law, or a series of power, right? In the independent variable. So this is a very interesting and important fact from what we're going to do next. But before, I want to give some examples for you of interesting functions. We could expend the whole day here, put the functions that are important in engineering in general and that are expressed in terms of power series. But I took a few here, just an example. So I took one algebraic type of function, 1 divided by 1 minus x, right? We all know that when x goes to 1, this explodes, and this explodes. And if I add up ones forever, this explodes as well. So everything is fine here. And this is a very interesting series because it's just the sum of the powers. This is the sum of the power with an independent term. So this is the independent, right? So m here, when I don't put here in this summation symbol, when I don't put anything, you know that is the index that is evolving. So here is an interesting series where the coefficient is all 1. And it is a very easy power. 1 plus x squared plus x cubic plus... And this is a very interesting function. It's a function has a very interesting behavior around x equals to 1, which the function is 1 divided by 1 minus x. Okay, and this is, you may recall the geometric series. If you understand here, I took the first term as 1, and I took x as a multiplication. So each term is the before term times x. So that's how you build up the series, and this is called geometric series. And it has a specific form. So when you add anything that's 1 plus x squared, x plus x squared, this is the called geometric series, and the whole sum is 1 divided by 1 minus x, provided some conditions for x here. Right? Okay, no, but there is some other functions that can be expressed in terms of power series, like the trigonometric function. Nobody questioned that trigonometric functions are very important indeed. And I took the cosine of x, but you could take any trigonometric function, and equivalently, they can be expressed in series. And the cosine of x, it is a series, a very interesting series where, you know, you have even here the coefficient, right, that we are putting is here, and it starts from 0 up, so you have always an independent term when x equals to, when m equal to 0, right? So you have this independent term, because we all know that when x equals to 0, the cosine of 0 is 1, and if everything here zeroes out, means that the 1 remains. And this is a nice series, you see, because appears the factorial here, that we all know the concept of factorial, appears the powers, they alternate, but it's very interesting because in series, normally the parity and the symmetry of the function is present on the series. So we all know that cosine is an even function. Therefore, only even terms appear. Square to the 4th power, the next will be to the 6th power, and so on. Because we know that changing the sign of x does not change the function at all. So the series knows that. There is another function that's very important, is the exponential function. It's appear everywhere, right? And the exponential function is also a very interesting series. It's a series that exponential of x is the series that's x to the m power to the m divided by m factorial. So 0 factorial we know is 1. 1 factorial is 1 as well. So I have 1, I have x, and then I have x squared divided by 2 factorial, x to the cubic divided by 3 factorial, and so on. So that's also another example of an important series, which is the exponential function. And you all know that when x is small, these terms is not important, and we have the famous expression that exponential of x is 1 plus x, basically, when x is very small. Okay, so those are a few examples of series functions, well-known functions, expressed in series, in power series, right? Because we can even go further and express express functions in terms of series of another functions, like cosine or like exponential or like anything else, as we're going to see in the next few lectures, right, when we're going to use the integral transformation to solve the differential equations. But this gives us, you see, the main goal here is to solve the differential equation. So that gives us everything we need, because we are looking, when we are somehow solving a differential equation, we are basically looking for a function. At the moment, ordinary equations, functions of a single variable, but maybe the function is function of many other variables, depending on many other variables. That's what we're going to call the partial differential equations that's coming later. This gives us a very interesting possibility, because since we know that any function can be expressed in terms of a series, and we are looking for a function in the solution of a differential equation, we can start the process of solving the differential equation by considering the function expressed in the series, in the power series, instead of looking for a function in general. Of course, we know the power, you know. We know that those are x to the 0, x to the 1, x to the 2, and so on. If we somehow can determine the coefficients, we know the function all. We know all the series, we know all the function, right? The only thing is we know the function expressed in series. If it is a series that we can identify the analytical form of the function, we can go back and we can somehow determine the function, express the function the way we express here, if it is an exponential, or we can leave it as a series. It is a legitimate mathematical expression, this series, right? So this is what we're going to do. We're going to introduce to you this powerful method, which is power series for solution or for solving differential equations. And this is a method that we use always. You know, in physics, for instance, in quantum mechanics, if you don't have this method, we somehow have a lot of problem to identify solutions of the spectrum of energy in many, many situations. So, having the differential equation here, I put a generic form of a differential equation. Of course, I put like a second order differential equation, but what we're going to say here, what we're going to do now, is valid for any differential equation that you may have in your problem. I took an example, a second order differential equation which has a second derivative. We all remember that when I say y double prime, what I mean is d2y dx2, right? This is the notation. When we say y double prime means second order derivative of y. If I say triple prime and so on, if I single prime means first order derivative, no prime means no derivative. And we want to solve this equation. As I told you, I took a second order, but you can take it of any order. There is no problem with that. And we're going to use for this an example of power series. And I'm going to take this because second order differential equations are the ones that appear a lot. And then I took as an example to explain to you how we're going to deal with the problem of power series. Because the first thing we're going to do here is say, okay, this is the differential equation, right? That's the equation I want to solve. I have this differential equation. If I have this differential equation, I'm going to say that there is a solution, so exists a solution. A solution exists, and it is y of x. I'm going to say that this solution is a power law. And is a power law where I do not know the exponent, the coefficients. I could say that this is a power law of x minus x0 to the m power. Nothing really changes here. right? If I say that this is the solution, so that place it in the original equation. So when I take this solution and I put in the differential equation, it must be a mathematical true expression, right? And the only problem I have now is to organize with my boundary conditions, my initial conditions of the equation, because normally they're going to say, we are looking for a function, and as x equal to 0, y should be this. So always we have a initial condition for the differential equation, right? Okay, and the whole problem now is to determine the set of coefficients that composes the series. This is the problem. If I know that, I know the solution for the differential equation. So what are we going to do? We're going to exactly concentrate, and I'm explaining to you step by step how imagine the solution as a power series. How can you solve the differential equation? And it's very simple, because now instead of be dealing with derivatives, we'll be dealing with powers. And we know very well how to deal with powers of x, or power of the variable here, right? So this is the essential point of solving a differential equation using power series. Is imagine the solution as a power series and try to find who are the coefficients. In many situations, we're going to find that these coefficients, due to the boundary conditions, due to the conditions that are given to that this function must obey, it has only a few coefficients that are valid. The other ones do not exist. So this is a finite polynomial, right? You see, we find that all the time. But it may be infinite polynomial. So there are important functions that are expressed in series, like Bessel functions or spherical harmonics. Are functions that we use in electromagnetism all the time. There are series that goes forever. But in determinate problems, when we have a specific situation, maybe only a few coefficients can exist. So when we say that we are solving the equation as a power series, does not mean that the solution will be an infinite power. Sometimes it's a polynomial. We find exactly a finite is a series, but it's a finite series. It's not an infinite series. Okay? But what you gotta understand here is that if we express the function that way, when we determine the collection of coefficients, we are determining the solution of the equation. And this is the essential point of solving differential equations using power law. Of course, now instead of being worried about the function, we be worried about the coefficients. That's the only thing that changes, right? And I'm going to take this equation as one example, and we're going to express the solution in power, and of course we're going to have to input in this equation. We're going to have to input the variations of the power series. But to do the variations of the power series is not hard, it's very simple. So let's consider this function all the time now. All the time, this is the equation we have in mind. Having that equation in mind and establishing that this is the solution. So establishing that this is the solution, right? The function, of course, I'm expanding now. I'm putting in an expanded form this series. So what we have? We have that the function itself. So we all know the function, the equation that we are trying to solve. And we propose a solution this series. In this equation, in this original equation, we're going to have the double derivative, the single derivative, and the function itself. So from the series, we must express who are the second derivative, the first derivative, and the function itself that we already have done. The function, when I put, I'm expanding now, so you're going to understand a little better what I'm going to do. The function itself is this, is C0, the first term, C1x plus C2x squared plus the other terms. When I take the derivative of a polynomial, everybody knows how to take a derivative of a polynomial. You just put the exponent here and subtract 1. And if it is a constant, we all know that constant does not vary with any coordinate, so it's 0 the derivative. So when I take the first derivative of this series, I got, well, the first term disappears. And then the first term that appears is the derivative of C1x, but the derivative of C1x is C1. And then the derivative of C2x squared, the 2 comes here, and then it's 2 times C2 times x, because now it will be 2 minus 1. Of course, we are using the property that the derivative of a sum is the sum of the derivatives. This is a well-known property that we learn in basic course. And so on. So we're taking the derivative of each term. So the first derivative of this series is this expression here. And then you know that numbers start to appear in front of the series. But if I want to go to the second derivative, then, this was the 0 order. I took the first derivative, I end with this series. Now I go and take the second derivative, which means take the derivative of the first derivative, of course. And then this term disappears, and then the first term that appears is the 2 times C2. And then here comes another 2, so it will be 2 times 3, which is 6, C3 times x to the 1, plus the other terms. So we keep doing this forever. So you see, now each member or each part of the differential equation is a whole series. And we can express, as we normally like in mathematics, express the derivatives in a generic way. So you should observe that if I express y as a series, the first derivative will not start in 0. We start in 1, right? The index will start. The index of the original function start in 0. But since the constant will disappear, when I take the first derivative, there is no sense in start from 0 because I know that that term is not present. So then we start in 1. If we start in 1, we can express the first derivative as a sum as well. And this will be Cm times m times x m to the minus 1, because I took the derivative of this, the m came here, and subtract 1 here. And so on, the second order, second derivation. The second derivative of this is taking the derivative of this. So now, but then the term 1 will disappear, because now the term equal to 1 is a constant. So I start my series in m equals 2. I start in the second term only. Or it will be in the third term if I consider 0 as a term. And here I have this. When I take the derivative, this exponent comes down. And I subtract another one from m minus 1. That will give me m minus 2. And the series starts now in 2. This one starts in 1, and so on. So you see, I have a whole expression of series that represents the derivatives. And now I take all this. So how is the procedure now? So I have this series that should happen. I don't know the coefficients, but I know that when I put in that original equation that I want to solve, so when I put in the equation that I want to solve, that's still a true mathematical expression. If this is the solution, so I take this and put in that. Taking the derivatives the way I present to you and putting in the original equation, you're going to have a expression, a mathematical expression, that do not have any more derivatives, only powers of x's. So what we do to solve the equation using the power law. We basically substitute in the equation all the terms of the equation by the derivative of the series. And we're gonna get a relation between m's. We're gonna try to extract from the fact that that equation represents a true mathematical statement. We're going to get how the coefficient should be. But you have to remember that when you substitute in the series or in the equation all the derivatives, all the series that represents the derivatives, we're going to have a huge mathematical expression with many powers. And then you have to remember a very important fact from basic algebra. You have to remember that when we have a statement that many power law equal to something, another power law, the same power coefficients must be equal. So if I have an expression that says that C0 plus C1x plus C2x squared plus and so on equal to A0 plus A1x, I can guarantee to you that all the coefficients of the same power of x are equal. So C0 must be equal to A0 because the same power 0, right? X to the 0. C1 must be equal to A1. C2 must be equal to A2. So all the coefficients of the same power must be equal. And that gives us a series of equations that will relate the coefficients, allowing us to obtain the coefficients from those relations. Sometimes by knowing one coefficient, which is one initial condition, I am able to obtain all the coefficients of the series, even if they are infinite number. If I have an infinite series, I'm able to solve and to build up the series as a whole. So you understand, right, what we're going to do. I'm just going to, before I start the examples, I want to review to you that what we're doing here is we have an equation. We want to solve this equation. And we are saying that the solution is a power series. And now we need to determine the coefficients. But the first thing is we need to use the equation as the mathematical statement of reality. So this is a true statement. So we have to obtain the derivatives. This is a second order, but as I told you, this can be generic. You can use any order you want of differential equation. So we say, okay, if this is the solution, the derivatives are given by those expressions. Having those expressions, we go back to the equation. And then we're going to substitute. Whatever I have the function y in the equation, I'm going to put this series. Wherever I have the first derivative, I'm going to put this series. Wherever I have the second derivative, I'm going to put this series. And wherever I have any order, I could keep going depending on the order of the equation. And then I'm going to have a huge expression that the equation now is turning into a polynomial equation. And I know some facts, right? And the facts I know is that when I get a huge equation, all the coefficients of the same power must be equal. If for some reason I have a huge equation that's equal to 0, means that any order coefficient has to be 0. So I build up a polynomial equation, but I have some rules to solve. Because I'm going to start to find relations between those members. And that's very interesting because since the derivative, the mixture, mixing, the derivative mixes different coefficients. So we're going to mix C0 with C1, with C2, and so on. I'm going to have a relation between the coefficients. And normally, those relations allow me to obtain what are the real coefficients involved. And once I know the real coefficients involved, I know the solution. So the scheme is, imagine you have a series, substitute the series in the equation, the original differential equation, taking the derivatives, and now you're going to make the relation between the coefficients. And once you do that, you are able to obtain the coefficients. And once you obtain the coefficients, once you obtain the set of coefficients, you solve the equation. That's the Gloria. You solve the equation. And this is what we're going to do. So I already explained you the method. Now, in the next lecture, I'm going to solve some examples. So please don't miss the next lecture in this tutorial of differential equations. See you then.